Hello class 10. In today's video we are going to learn about specific resistance, also known as resistivity. In the previous class we have learned that resistance is directly proportional to the length of the wire, which means that R is proportional to small l, where R represents resistance and L represents the length of the wire. Secondly, we also learned that resistance is inversely proportional to the cross-section area of wire. This means that R is proportional to 1 by A, where again small a represents the area, cross-section area of the wire. Now we know that since a wire has circular cross-section area, so A can be replaced by 1 by pi r squared. So R is proportional to 1 by pi r squared. Now combining the first relation R proportional to L and the second relation, that is R proportional to 1 by A, we get the combination of the two. We get R proportional to L by A. Now whenever we have to replace the proportionality sign, then it will be replaced by an equals to sign, and then we have to write a constant. So over here R is equal to rho L by A, where rho will be the constant. So R is equal to rho L by pi r squared, where rho is a constant, and this rho, the constant, is called as the specific resistance, or also known as resistivity of the wire. Now specific resistance, from the above relation we can find out that rho is equal to Ra by L. If you take this A this side, it will be multiplied with R and L goes to the denominator, so you'll get rho equals Ra by L. Now if L is equal to 1 and A is also equal to 1, then we get that rho is equal to R. Means the specific resistance becomes equal to resistance of the wire if the length of the wire is 1 unit and area is also equal to a unit. So a specific resistance of a material is the resistance of a wire of that material of unit length and unit cross-section area. So next we discuss about the unit of the specific resistance. As we know that rho, the specific resistance, equals to Ra by small l, so replacing this we get unit of rho is equal to unit of R times unit of A divided by unit of L. Unit of resistance multiplies unit of area divided by unit of length. We know that unit of resistance is ohm, unit of area is meter squared, and unit of length is meter. So when we simplify this, meter over here cancels the square on top, so we get ohm times meter, or in short, if you write it by the symbol, then ohm is written as omega and meter as m. So it is omega m, or simply ohm meter. Now the factors affecting the specific resistance. Number one, it is different for different substances. Means the specific resistance for copper will be different than the specific resistance of silver, and it will be different than specific resistance of aluminium. So different substances will have different specific resistance. So if there is a substance which is insulator, then they'll have very high resistivity, about 10 to the power 13 ohm meter. If there are semiconductors, then they'll have low resistivity or specific resistance, about 10 to the power minus 5 ohm meter, and the metals will have very low resistivity, about 10 to the power minus 8 ohm meter. Number two, the specific resistance also depends on the temperature of a substance. For metals, it increases with the increase in temperature. More you increase the temperature, then the specific resistance will increase more for metals. But for semiconductors, it decreases with the increase in temperature. If you increase the temperature, then the specific resistance decreases for semiconductors. Next, we move on with conductivity. Conductivity is considered as the reciprocal of resistivity, and it is represented by the Greek letter sigma. So over here, this is a Greek letter sigma. So sigma represents 1 by rho, that is the reciprocal of resistivity, and since rho is equal to Ra by L, therefore 1 by rho is equal to L by Ra. Thus the SI unit of conductivity will be 1 by ohm meter, that is ohm inverse meter inverse, or it will be omega inverse by m inverse. Now this omega inverse or ohm inverse is written as Simon and meter inverse is per meter. So it is Simon per meter, the unit of conductivity. Now for different purposes, we use different kind of material. So it's a choice of material that we have to choose wisely for different purposes. Number 1, the wires used for electrical connections must have low resistance. If you're using the wires for electrical connections in your household circuits, or for different purposes where the current needs to flow, then you have to use the electrical you have to use those wires which has very low resistance. Example, copper, aluminium, etc. If you are using the wires for resistors, then they must have high resistance and their value should not change with change in temperature. Examples are manganese and constantan. Fuse wires, which are made up of alloy of lead and tin, has very low melting point and they're higher resistivity than copper. So when excessive current passes through, it gets heated up and melts, cutting off the connection from the rest of the electrical appliances. So the fuse wire, their specialty is that they have very low melting point. The filament of an electric bulb, which is made up of tungsten, has very high melting point. Thus, it does not melt even at 2800 Kelvin. At that temperature, it gets very hot and thus it glows and starts giving light. The heating element in appliances like heater, toaster uses nichrome wire as their resistivity is high and gets heated up. The resistance increases with the increase in temperature. Superconductors. Resistance of some substances decreases with the decrease in temperature, and they are almost equal to zero when the temperature reaches near absolute zero. Means that the resistivity becomes almost equal to zero. Now resistivity is almost equal to zero means the conductivity is the inverse of resistivity. Therefore conductivity will increase and it will become infinite. So the definition for superconductors will be, they are the substances of zero resistance or infinite conductance at a very low temperature. Now this very low temperature means really low. It should be almost close to the absolute zero. So mercury, lead and niobium, these are the superconductors at temperatures very close to absolute zero. Okay, it must be like 4 kelvins or 5 kelvins, somewhere around at those values of temperature, that this mercury, lead, niobium, these elements will act as superconductors. But practically, since it's not possible to attend that much low temperature, so the superconductors are not practically usable. Okay, so with this we come to an end of our video. And the next thing is, if you have any doubt, just let me know through your mails. Thank you.